Back with you on example number 3, which is an example of a completely inelastic collision, or perfectly inelastic. That means that the two things are going to stick together when they collide. So using our smart carts, that would be like when the Velcro ends are running into each other so that the carts become attached after they collide. So here I've got a little one pushed towards a bigger one. The bigger one's at rest. The smaller one is moving at velocity v. They collide and stick together. And so here's the smaller one, and it's stuck to the bigger one. And I would guess that they move to the right after they collide and stick together, and I'd also guess that that velocity would be smaller than this velocity. So I'm going to draw one arrow to the right, but I'm going to draw it smaller than this arrow right here. And I'm just going to call that v prime. I'm guessing that's something I'm going to be asked to find here in just a second. And I don't need a subscript because there's only one thing at this point. They're both stuck together. So again, we're going to play that game where we draw the horizontal location, the center of mass of the two-cart system. It probably would not be directly in between them, but it would probably be shifted a little bit more towards the heavier cart. So I'm going to do like about there. And then the same thing would probably be true after the collision. It's going to be more towards the heavier object, kind of like that. We drew a picture showing how they're moving after the collision. That's something we should always do. That's going to help us like make predictions and see if our answers are reasonable or not. We did that part. Derive an expression for the final velocity of the 2M cart and indicate its direction. So let's use momentum conservation to do that. So I'm going to say that the momentum of the system is equal to, the first cart has a mass m and velocity v. It's going to the right. And then plus, the second cart has mass 2m and it's got a velocity of 0 because it's at rest. And so the total momentum of this system, mv plus 0, is just m times v. And then again, I know that the momentum is going to be conserved because there's nothing outside interfering. So I'm going to say that equals p system prime, kind of like that. After the collision, I can kind of treat these as one object since they're stuck together, moving at one speed together. So I'm just going to add the masses up. I'm going to do that real clearly. M plus 2m, like that. And then times that combined velocity of all of them. So the momentum of the system is just the momentum of this one thing. It's got mass, well, m plus 2m is 3m. And then velocity v prime. And again, I can say that that is equal to m times v because that was the momentum before the collision. So doing a little bit of algebra, I can get that v prime is equal to, well, the m's would cancel out, and I would just divide both sides by 3. So v prime equals v over 3, and then the direction's important. All that stuff is still moving to the right. So my guess up here that this velocity would be smaller than this velocity is true. 1/3 v is smaller than v. Part E wants us to derive an expression for the energy lost during the collision. So again, remember that the kinetic energy is given by K equals 1/2 mv squared. So the kinetic energy of my system before the collision, well, the m cart has kinetic energy because it's moving. So 1/2 times m times v squared. The 2m cart doesn't, though, because its initial velocity is 0. So if we add 1/2 mv squared, that's literally what I get for the stuff in blue, to 0, then I just get 1/2 capital M v squared. After the collision, so Okay, system prime. I've got one object of mass 3m. And it's moving at velocity v over 3. And then I've got to square that. So doing some simplifying here, I've got a 2 on bottom, 3m like that. I need to square all this stuff, so v squared is just v squared. And then 3 squared on bottom would give me 9. And then I could simplify that a little bit. 3 over 9 would be like 1 over 3. And then 2 times 3 would be 6. So I get mv squared over 6. So the number in green here, light green on the right, is smaller than the number in dark green on the left. Energy was lost during the collision. That energy would go mainly to heat and sound. Like when these things collide and stick together, you can hear it. That's where that energy comes from. So to find the change in energy, I want to know how much is lost. We're just going to do final minus initial. So 1/6 mv squared minus, I'm going to go ahead and get a common denominator. So I'm going to write that as 3/6 mv squared. So 1/6 minus 3/6 would be like negative 2/6 mv squared. Or I can reduce that to negative 1/3 mv squared. So what that means is that I've lost, because it's negative, 1/3 mv squared energy lost during the collision. So the best way for right now would be to just write it like this. I lost this much, and I know it's a loss because of that negative side. I had a lot of energy, and now I have just a little bit of energy. Energy was lost. That's typical of an inelastic collision. Any inelastic collision, there should be some energy lost. In the next example, we're going to look at an elastic collision and see how that is different. Till then, ta-ta.